Okay, this is a numerical where we have to draw the BMD and SFD for the beam shown in this particular figure. The main difference from what we saw in the previous numerical and this is that we have a inclined force here on a crank, right? So what we do today for the inclined force, we'll be doing the same thing for even the point loads that are applied on the beam, right? So I'll explain that later. Now let us start with this numerical. Okay, the first thing we need to do is, since you have an inclined force here, I will first convert this inclined force into, I'll resolve this into horizontal and vertical directions, right? I'll resolve the force into horizontal direction and vertical direction. Yes. So for this, what I will do is, I'll start from here. Resolving this 5 kilonewton force into horizontal and vertical force. Let us say the point here, I'll first name this point as A, B, C, D, E. Let me call this as F. Okay. Um, Resolving the load, inclined load at point F into horizontal and vertical directions, right? So I'll name this as WF V, that is vertical direction force. So this is inclined at 30 degree. So the vertical component of this will be 5 sine 30. So sine 30 is half. 5 sine 30 will be 2.5 kilo Newton. And W F at point F in horizontal direction is 5 cos 30. So let me calculate that. 5 into 30 cos 4.33 kilo Newton, right? Now these two forces, I'm changing this 5 kilonewton force, which is inclined at 30 degree, to one horizontal force equal to 4.33 kilonewton and one vertical force equal to 2.5 kilonewton, which is acting at point F. Now, what is the effect of these two forces? We will see, right? First, let me consider the vertical component. Consider the vertical component. Now, vertical component is acting at point F here, right? So, directly this force can be applied at point B, right? So, the first result of this is, um, apply a point load at point B of magnitude how much? Vertical forces 2.5 kilo Newton, right? That is the first thing that we do with the vertical force. Second thing we do is, so this vertical force is acting at a distance of 1 meter from B. So because of which there is a, it is acting like this. So it is clockwise moment. So force into distance will be the value of that couple. So a couple equal to, how much is the force? 2.5 into 1 is equal to 2.5 kilonewton meter is applied at point B in clockwise direction. So this is downwards and it is making a clockwise couple, right? That's why I've taken this as clockwise. Now we have to consider the horizontal force. Consider the horizontal component. So horizontal component also you will apply a point load of 4.33 kilonewton at point B along the beam, right? What do you mean by along the beam? See, the horizontal component is along this direction, right? So here you have to apply force in this direction from C to B. There will be force equal to 4.33 kilonewton. Now this force will not result in any BM or SF. There is no shear force or bending caused because of this. This will only increase the tension in the beam, right? So this is not going to result in any BM or SF, so I will ignore this. The second thing that happens because of horizontal component is a couple equal to, the magnitude is 4.33 and this is in horizontal direction. It is applied here at point F and from B it is 1 meter above here. So this is making a reverse couple, counterclockwise couple. So 4.33 into 1 and that is equal to 4.33 kilonewton meter in CCW, counterclockwise direction at point B, right? So I have to replace this entire thing with these four things in my load diagram. So let us draw the load diagram first. For this, I'll first project all these points. So all the salient points that are there, I'm just projecting it. Okay. Now I will just try to copy this much. I'm just trying to use the same sketch so that I don't have to spend more time. So I will remove all this. Okay, I'll just take this and put it here. Now I have a vertical force. So I will apply this vertical force at point B, and the magnitude of that vertical force is 2.5 kilonewton. So here it is 2.5 kilonewton, and you have a couple acting at this point. Now, if you see at point B, I have two couples, correct? One is 2.5 kilonewton meter, another in clockwise direction, and another one is in 4.33 kilonewton meter in counterclockwise direction. Now, what you have to do is, if both were to be same direction, now let us say this were to be clockwise or this were to be counterclockwise. Since both are acting in the same direction, you can just add them together and apply the total couple at this point. Now, since both of them are in opposite direction, we have to take the difference of these two couples, right? Now 4.33 minus of 2.5, right? So whatever you get, now the sign or the direction of the resultant couple will be the direction of the maximum couple. Now this 4.33 is in clockwise, counterclockwise direction, which is greater than 2.5. So the resultant couple at point B is equal to 4.33 minus 2.5, that is equal to 1.83 kilonewton meter counterclockwise direction, right? So I have to show that here. Let me just do that. Right? Counterclockwise means anti-clockwise. It should rotate like this. So I will erase some part of this, and I will show a arrow like this. Right? So this is rotating in counterclockwise direction, and the magnitude of this is 1.83. Here I'll write 1.83 kilonewton meter. Right? There is also a horizontal force. If you want, you can show that at this point of time, sorry, at this particular point, but that is not going to result in anything in your BMD or SFD. So that is why I'm not showing that. It is not required as such. Now I will also show the reactions. So at point A, you have a support. So you'll have a reaction here, and again at point B, I have another support where you will have the reaction. So my load diagram is complete now, right? So this is the question that was given. So this is the modified load diagram. Okay, modified load diagram. Now you can solve this numerical. So what you have to do first, you have to find the support reactions. So let me first take bending moment about point A, taking about point A. You have the sign convention. Right side counterclockwise is positive. So this is RD here. So I write RD into 2 plus 2 plus 2 is 6 meter. There is also a counterclockwise couple of 1.83 plus 1.83 minus, you have this UDL, intensity is 4 into length is 4 meters into, it is acting at this point D, that is the midpoint of CE. So from D to A it is 6 meter into 6 minus this point load of 2.5 into perpendicular distance is 2, and this is equal to 0, right? Now if you calculate this, you will get the RD. These two negatives will go on the other side as positive. So 4 into 4 into 6 plus 2.5 into 2 is 5 minus 1.83. That is 99.17 into 6 is there. So by 6, 16.528. RD is equal to 16.53 kilonewton, right? Now if you add, we also need sum of all the forces equal to 0. Also RA plus RD, that is the upward force, that should be equal to 2.5 plus 4 into 4. So 2.5 plus 16 is 18.5, or RA 18.5 minus 16.53 is 1.97 kilonewton, right? So we got the reactions at RA and RD, and let me just write that down here. RA is equal to 1.97 kilonewton, RD is equal to 16.53 kilonewton. See, wherever you have more load on the beam, you should have larger reaction force. So here you have UDL, which is 4 into 4, 16 kilonewton. That's why you have a reaction equal to 16.53. Whereas here you have load close to this is only 2.5. That's why you have lesser reaction at this point. Okay. With this, we are done with the reactions, support reactions. That is your step number 1. Second thing is we have to start with the shear force, calculation of shear force, right? So shear force diagram. So for shear force diagram, let me start from point number A. So SFA, you can do like this. Wherever you have sudden raise, LHS is equal to 0. You start from 0, then you have vertical force of 1.97. So SFA RHS, LHS RHS means on the left hand side of point A, immediately on the right hand side of point A, right? So suddenly at that point the force is increasing, is equal to, I have a positive force 1.97 kilonewton. Then SFB LHS. Between A and B there is nothing, there is no UDL or any other force, so it will remain same, is equal to 1.97 kilonewton. SFB RHS is equal to now 1.97 minus, I have a 2.5 kilonewton force acting downwards, 2.5. So 1.97 minus 2.5 is minus 0.53 kilonewton, right? So that means it is going below the zero line. Now again between B and C there is no force, so SFC, LHS, RHS both will be same. So I'll just write SFC is equal to minus 0.53 kilonewton. Then come to point D. So SFD, here I have a vertical force, so there will be sudden change. So you will have LSH RSH here. LSH is equal to minus 0.53. You have to take the previous value always. So minus 0.53. Now between C and D I also have a UDL. The intensity of this UDL is 4 kilonewton per meter. This length is 2 meter. So the total force between C and D, total load between C and D is 4 into 2 equal to 8. So minus 4 into 2. So minus 0.53 minus 8. That is minus 8.53. Minus 8.53 is the force here, right, on the LHS, kilonewton. Now SFD RHS is equal to, take this value now, minus 8.53. Always take the immediate previous value for calculating the next shear force. So from this I have to subtract this much, right? No, it is addition, it is upward force, so you have to add it here, plus 16.53 plus 16.53 is equal to 8, right? So this will be 8 kilonewton just a minute. Okay, now I have come to D, and the last point is E. SFE L. Okay, this is a end point, so it is going to be 0 there. We will not have 2 points. So SFE is equal to previous value is 8 minus, between D and E again I have uniformly distributed load, UDL, 4 into 2, minus 4 into 2. 4 into 2 is 8. 8 minus 8 is 0 kilonewton. So I have completed the shear force diagram. See, you should get this ends correctly, right? When you draw the shear force diagram, you should get this correctly. If you start from here, it is 0 here, again it is increasing. Like that, if you go at this point, you should get at this point 1.97. If you are not getting that, then you are doing mistake somewhere, right? You can cross check always. Now we have to draw the shear force diagram. First let me draw a horizontal line. This is representing the zero shear force value. The maximum value here is 8.53 on the negative side and positive is 8. So let me start from here. This is 0. uh, at point A I have two values. It is increasing from 0 to 1.97. So let me just show this here. This, I'm assuming this is 1.97. From here to here it will remain constant. SFB LHS is 1.97, RHS is minus 0.53. So there is a dip here. Alright. Now between B and C, again it remains constant. Just draw a horizontal line like this. At C to D, there is a UDL, because of which the shear force varies linearly, minus 8.53. So let us show minus 8.53 somewhere here. Then at D again there is one more, which is plus 8. So it increases to plus 8 here, and then at E it is 0, 0, right? So this is your shear force diagram. Now you just have to put proper sign here. This is positive, this is positive, this is negative. Since in between C and E where I have the UDL, there is no point where the shear force is equal to 0 and the sign is changing. ऐसा कहीं पर भी नहीं है in this entire beam. So I don't have to find the location of maximum bending moment in this case, right? Also just write down the values on the shear force diagram. This is 1.97 kilonewton. This is, don't have to mention the sign 0.53 because I have already mentioned here plus and minus. So this is 0.53. This value is 8.53 kilonewton. Here also it is kilonewton. Right? And this is 8 kilonewton, and this is of course 0, and this is also 0. We started with 0. So this is SFD. I have completed my shear force diagram. Now you have to start with the bending moment diagram. Now for drawing the bending moment diagram, I need to first calculate the bending moments. Let me just move this little down because I need the load diagram nearby for calculating the bending moment. Okay, so I will do this here and then put it down. Right, now start from left hand. See, there are some numericals where the overhanging comes on the right hand side. So if you are comfortable from that, also you can do it that way. My suggestion is always start from left hand side so that we don't miss anything. Okay, so B bending moment diagram. So you just have to calculate the bending moment at all the points. BMA is equal to 0. Why? End support. Okay, unless you have a couple at the end, you will not get bending moment for any of the beam. Okay, for simply supported beam or overhanging beam. For cantilever, you will get it in the support. Okay, next point is I'll come to B. Now at B I have a couple here. So you have to take bending moment from left side and right hand side, uh, and at that point there will be a steep increase or decrease of bending moment. So BMB LHS is equal to, I'm considering left hand side. So this is upward force. This is making a clockwise moment about B. Left side clockwise is positive. So 1.97 into distance is 2 meters. So 1.97 into 2 is 3.94 kilo Newton meter. Alright. Then I have BM at B considering right hand side. Another thing is the difference of BM at this particular point B, LHS and RHS, the difference of this should be equal to the couple 1.83, right? If you're not getting that, then you have done some mistake. So I'm considering the right hand side now. So right hand side I have this reaction first, so that will be positive 16.53 into perpendicular distance is 2 plus 2 4, and I have this UDL which will be downward, so that will be negative 4 into length of UDL is 4 meter, and it is acting at this point D. So from here to B the length is again 4 meter, so into 4, and that is equal to 16.53 into 4 minus 4 into 4 into 4, 2.2, sorry, 2.12 kilonewton meter, right? So it has decreased from this value to this value, and if you want you can check this also. 3.94 minus 2.12, sorry, 3.94 minus 2.12 is 1.82, right? So I don't know how it is happening. Maybe in rounding off somewhere we have lost that point, not one, right? It should ideally be equal to the value whatever you have it here, right? Let's go to next point, that is C. Now from here onwards you can take any one side, you don't have to take both side. So BMC is equal to, I'll take left side only, so it is 1.97 into 2 plus 2 is 4 meters. This is making clockwise on left side, this is counterclockwise, so this will be negative, minus 1.83 minus 2.5 into 2. So let's calculate this. 1.97 into 4 minus 1.83 minus 2.5 into 2. So it is 1.05 kilonewton meter. Then BM at point D. Here I have only one force, that is UDL on the right side. Left side there are too many things, so I will take the right side. This will be negative because it is coming downwards, the force is acting downwards, and it is making a clockwise moment on the right hand side. So right hand clockwise is negative, so it will be minus 4 into the length of UDL between D and E is 2 meter, and it is acting at the midpoint of this DE, so into 1. So 4 into 2 is 8. It is minus 8 kilonewton meter, and BME will be 0. Why? Free end, right? So it's a free end, so the bending moment at this point will be 0. Now with this data I have to draw the bending moment. Now if you see between C and D, the value is changing from 1.05 to minus 8, right? So that means you will have a point of contrafluxure in this particular numerical. So we'll have to locate the point of contrafluxure also. Let us first draw the BMD, right? So take line, positive side, the maximum value is 3.9, right? So I will just draw a line like this. Okay, now at A, bending moment is 0. At point B, the bending moment, there are two values, 3.94 and 2.12. So first let me mark these 2 points. So let us say this line is representing 3.94, which is almost 4. So somewhere here I'll have this thing 2.12, right? So now the BMD, it will start from 0 here, 0 to 3.94. Then there is a sharp decrease in the bending moment, and then it will go on. BMC is 1.05, so somewhere half of this. Let us say this is 1.05, and at D it is minus 8, so it will be on the negative side. I'll increase this further. Right, let us say minus 8 is somewhere here. Okay, and here it is again 0. Now the BMD is this section C to D is UDL, so the variation will be a parabolic curve. So I have to join this by a curve like this, and from here to here also will be a parabolic curve. Okay, so this is your BMD. Now just mark the values here. This is 1.97. Sorry, I wrote the shear force one. BMB is 3.94 kilonewton meter. Then it is decreasing to 2.12 kilonewton meter. At this point it is 1.05 kilonewton meter. This is 8 kilonewton meter. Of course this is 0. This is also 0. This is positive. Oh my god, this is negative. Now this point is where we have the bending moment changing from positive to negative, and here the bending moment will be 0. So I have A, B, C, D, E, F. I will call this point as G, right? So G is the point which is in between C and D. So you have to find the bending moment here. So for this, what we will do is uh, we will just draw a line here, right? And I'm assuming uh, this length as x, right? So you have to find the bending moment at x or at point G. So how do you do that? BMG is equal to, this distance is x, and I have a reaction here, so 16.53 into x minus this length is 2, that is the perpendicular distance of that, minus 4 is the intensity of UDL, into x square by 2, that is the distance, right? So and this value is equal to 0. Now if you solve this equation, you will get the value of x. So that is the location of point of contrafluxure, right? Sometimes it may be asked specifically to find the point of contrafluxure in the numerical. Sometimes if it is not asked, if you are getting a point of contrafluxure like this, you have to find the value. How to find it? Just mark that location, take that distance as x, find the bending moment at that point, equate it to 0 and solve it. You'll get the value of x, right? So that will be the complete solution to this numerical. Is there any question?